why aeroplane tires are made of special material which are conducting in nature, Now, you know that when aeroplane takes off from the runway, it goes to very large altitude, it passes through the clouds, and we know that clouds have normally charges. So due to this friction between the wings, also we know that the aeroplane body is metallic, made of aluminum alloys. So this will acquire charge. Now once the aeroplane acquires charge on its body, and when it is going to land, for example, it's landing. So what happened is, because of the excess charge, maybe negative or positive, which have been picked up by the aeroplane wings or the tips, which are very sharp, there can be sparks which can be created between the ground and the aeroplane body. So these sparks can have high temperatures, which can ignite the highly inflammable fuel, which is the aeroplane, fuel, and this discharge action, which will produce it's going to produce high temperature, can lit up the fuel and the aeroplane can catch fire. Now instead of that, if I have conducting tires, what happens is all the excess charge which has been accumulated during the flight, all the excess charge which has been accumulated by the aeroplane during the flight can be grounded, and all the excess charge can flow into the earth, and the body of the aeroplane can become neutral, and we can prevent this discharge which can happen between the aeroplane wings or the body in the ground, and even this fire hazard can be prevented. Yet another question here, there's a similar question here. Putting lightning conductors. Now we know that during the thunderstorms, when a charged cloud is passing over when a charged cloud is passing over a high tower, we need to put a lightning conductor on the top, so that whenever the lightning strikes, it first strikes the lightning conductor, and this is basically a conduction path up to the earth, and all the charge is dumped into the earth without the building becoming, a building catching fire, or some kind of a hazard happens, or the building can break because of that extremely large amount of charge which is dumped through the building directly. And moreover, we'll also discuss later on why these lightning conductors are made sharp. Why the lightning conductors are made sharp. Now, this particular aspect of why it is made sharp, or the tip is made sharp, would be discussed when we discuss about electric potential in the next chapter, and you'll become very clear why the lightning conductor's tip has to be sharp, so that it takes on all the charge and all the charge passes into the ground. Now, we are shifting to a very major topic of this particular chapter, but before that, you might have studied in your gravitation chapter how 2 point masses attract each other. Similarly, it was Coulomb who found out what is the nature of the force between 2 point charges. Now we are today going to discuss about Coulomb's law. Of course, electrostatics. So we're talking about the force existing between 2 point charges which are stationary, kept at some distance in vacuum, and it was Coulomb who found out that if you take 2 point charges, say Q1 and Q2, kept at some distance r in vacuum, then there is an electrostatic interaction between them. Q1, say for example, let us assume that both are similar charges, let's say that both are positive, then Q1 will repel Q2 with some force, let's call that a force is F21, force on 2 due to 1. Similarly, Q2 will exert a force on 1 by the Newton's third law, that is F12, and as you're able to see that because they are repulsive, they have to be equal and opposite in nature. So therefore, we have got F12 vector is equal to minus of F21 by the Newton's third law. And Coulomb found that when he was trying to find out the nature of the force between them, he found that the force, let's assume that the magnitude of these forces, F12 mod minus of F21 mod is equal to, let's say, this F, where F is the magnitude of the force, and we have seen that the directional force is along the line joining the two charges. Both are being positive, we assume them both of them positive, so they are repulsive in nature. So this force, he found out that, first of all, this force was directly proportional to 1 by r square, or this is inverse square force similar to gravitation. That means the magnitude of the force acting between any two charge is inversely proportional to the square of the distance between them. And secondly, the same force is also proportional to the product of the two charges. I mean, they are proportional, this force is proportional to both Q1 and Q2. Combining these two, we are going to get F is proportional to Q1, Q2 divided by R square. If it is a CGS unit, we can directly equate it, but because we are following the SI unit, so we are going to take that this force is equal to K Q1, Q2 divided by R square, where K is the Coulomb constant. Because F is in Newton, Q1, Q2 are in coulombs, and R is in meter, the value of K turns out to be equal to 9 into 10 to the power 9 Newton meter square upon Coulomb square. This is called as the Coulomb constant. There is one more expression for the Coulomb constant in terms of another universal constant which is more fundamental, and we'll write that K to be equal to 1 upon 4 pi epsilon naught. Now this is epsilon, this is a Greek symbol, and 0, I'm calling it as naught here. So either you can call it as epsilon 0, epsilon naught. Now using this value of K, if I basically find out the value of epsilon naught, then epsilon naught turns out to be equal to 8.86 into 10 to the power minus 12 Coulomb square upon Newton meter square. Now this epsilon naught is called as electric permittivity of vacuum. Now if I elaborately or completely write down this expression, instead of K, if I substitute this value of K in terms of the electric permittivity of vacuum, then I can rewrite this expression of force. Let me rub this off. This force, magnitude of the force, becomes equal to 1 by 4 pi epsilon naught Q1, Q2 divided by R square. So this is the Coulomb's law stated for vacuum.